we work across commodities, fixed income, rates, all sorts of different areas, and it's been a great experience. It's been there for about a year and a half. This part of the meetup is kind of focused on going over a data science interview question. We're going to try to keep it to 15 to 20 minutes, so that way we have enough time to go through Doug's presentation, and then also have some breakout time. Cool? Okay, so I think at the last meetup, I don't see anyone who was here at the last meetup. Alright, so I had one very straightforward question. I asked, can anyone explain to me degrees of freedom in layman's terms? Okay, so let's start there. Degrees of freedom is an incredibly important concept. I'm sure we've all discussed it when we're looking at P-tests and FCAT, and I think it's always a good thing to go over even the fundamentals, so that's what I think we should start out today. And if we have more time, I have another question in mind. We can kind of discuss that as well. Cool? Okay. So let's say I have 5 letters on the board, one for each day of the week, and I randomly want to pick out a letter for the day, right? And this is all going to tie into degrees of freedom, so please play along with me, right? So let's say you've got 5 letters on the board, one for each day, and the first day you pick out C, next day you pick out B, A, and D. So what does that leave? It leaves us 1 letter for the last day, right? So what were we allowed to vary in this example? Out of the 5 that we had, we were allowed to vary 4 things, right? We could constantly pick one or the other on any of the days. But on the last day, we were kind of stuck, right? We only had one option. That's the entire concept of degrees of freedom. So when you calculate a parameter like mean, you need to make sure you can vary, it's generally like n minus 1. You can vary n minus 1 parameters, and on the last parameter, you have to have that value. You have to, it's already pre-calculated because you've already determined what the mean is, right? So this is a very relevant concept when you're trying to look at various distributions and you're trying to understand how to interpret your tests. Okay, so most people understand this part of degrees of freedom, but can anyone tell me how we would do it for like discrete? How would we do it for, what's a good way to do this? I'm going through the examples in my head. Let's approach another problem where you have 2 variables, right? And they'll be like, let's say you're studying mice, and you say size versus diet, right? So in this case, you've got a little challenging, oh wait, I'll go to that example later, right? So we've kind of already gone over when we calculate means, right? This is very relevant for t-tests. Can anyone give me the formula for a t-test? Come on, somebody's quickly Google it. Help me.
On the Wi-Fi.
What?
Can't get on the Wi-Fi.
Well, you're excused, Harry, but I still expect you to know this. You got it?
Like average over volatility, and that's unbiased estimation of the vol.
Yeah, overall, standard deviation. You decide what the standard deviation is. If you're doing it for a sample, it's over square root of n, right? So it's slightly larger or something, right? So there you go. Or is it n minus 1 for a sample and n for a population?
I mean,
right?
there should be sample at vol and mean, right? And it's t. I mean, mu and sigma should be calculated from
sample. If it's not sample, it's going to be normal, right? It's not.
Would you speak up? I can't hear.
If it is not, it's a population, then you know.
Then you already know it.
We'll already know it's a normal distribution.
Right, right. Okay, so from a sample, I was just trying to make sure that n minus 1 was right. I hate being wrong about n minus 1 and n. It just bugs me, and it's always hard to remember when you have.
So should it be n minus 1?
What?
Should it be n minus 1?
It should be, I think, because the standard deviation is a little larger because you're doing a sample, so the n minus 1 allows you to increase the size of it. And the guy behind you is nodding. What's your name? Shin. Thank you so much, Shin, for backing me up there. Okay, so in this case, you've already determined your mu, right? Because that's one of the parameters in the case. So again, when we look at degrees of freedom in a t-test, you'll be n minus 1, right? Kind of the same way as we discussed, right? Cool. Now, let's look at a little bit of a harder case, which is the issue with a chi-squared test, where you have two variables, and you're making a box, right? So let's say I call this factor 1, factor 2, right? So I give you a box, and I put in value, and like, let's say I give you some cross sums, right? I'm just gonna put letters to not give it away. So given what we just discussed about degrees of freedom, how many degrees of freedom do you think we have here?
0.
You have 1 degree of freedom. Who said 1? Nice. Do you know why we have 1?
It's one. So we have two factors here, right? So
Right.
we can just have
Well, in the prior example where I had 5 hats, n was 5 minus 1 because I had 4 open things I could vary, right? So n is the number of values of like records of observations that you have. So, but close, but I think I want you to make sure that you get the concept perfect, right? So in this case, assume that I put in like 10 here, and I already had A, B, C, D already pre-calculated. In this case, you know that it has to be A minus 10, and then B is of course going to be, then you've got 10C, so then this is C minus 10, right? And then of course when you bring these two together, you should be able to get formulas for D and B, right? So how many things could I actually vary? 1, right? In this case, I could only vary 1. So what I'm trying to point out is you can't just always say it's n minus 1 when you're looking at degrees of
So
freedom.
what is fixed over there? So A, B, C, D are known, and you see how many.
Yeah, generally you'll know, right? Just like when you mean, you know what A, B, C, D will be,
And
right?
then in that last square,
What?
maybe they're not consistent between two, right?
Generally, these have to be consistent, they have to add up, the cross sums have to make sense, right?
Okay, so it's
Yeah.
okay.
So in this case, you only have 1 that varied. Cool, straightforward way to think about it. Degrees of freedom is incredibly important. Even when I interview, I often ask them, can you explain me degrees of freedom in a t-test, you know?
Is there
And
a
I think
formal?
it's a great way to just make sure someone actually understands the fundamentals. So now you know, you think about it in terms of hats during the days of weeks or the number of letters you pick out to label each day.
Is there a formal definition, like if you ask an interview, if you look for certain definition, or just like kind of way the like discussion?
The formal definition is there's one in Euclidean geometric space, but I think you'd have to look that one up for that. I generally just try to focus on the intuitiveness of like, why do I have one value that has to stay fixed, whereas the other ones don't, right? So generally, what I've seen in interviews is t-tests and chi-squared. And then like you could also talk about regressions. Why do you need more data points than the number of parameters in your regression, right? Because each factor starts off, but this was going to be the next part, right? So let's say I have a data set with 4 data points, right? Super small, super hard to get the data, don't know how I'm going to get it, right? And I decide to have 4 different parameters, right? When I create a regression, what is generally the first thing that actually happens in regression? You define the means, right? So in the hyperparameter space, I'm going to draw a 3 space, but assume it's 4, make it easy for me, right? The first thing you're always considering is like, okay, what are the means, right? Imagine like mean, right? That's where you generally start. Right? Whenever you look at a regression, you're trying to see how much better is regression than just a flat line across the entire data set, right? How much better is it than the mean? So again, you're defining something that has to be used, right? So when you have each parameter will then take up a degree of freedom, right? So eventually, you'll end up having to lock your data points. And so 4 data points with 4 parameters means that you have 0 degrees of freedom. You've got something's getting locked in every single, right? In every single space, you have to have some deterministic value to make sure that they all line up. And you can't be sure that it's going to be 1 point that fixes it for all 4 parameters, right? So in that case, this would probably be pretty bad because your degrees of freedom would be 0, right? So that's almost uninterpretable. So that's generally why people will say you definitely need to have more data than you have parameters in your regression. At least that's like my intuitive, simplified kind of, okay, like if I had to explain this in an interview, this is how I would think about it. Is that useful? Okay. So, are there any other topics that we want to kind of go over? Anything interesting someone's come across in an interview before I move on to my next question? Okay, sounds good. Looks like we're acing all the interviews and everything's going well. I'm happy to hear that.
I think those are the best questions. It's like if you were stumped on an interview,
Yeah.
and then you go back later and try to figure out what you should have said.
Right, and I'm not perfect. I Google this stuff beforehand. And I just write up my notes, practice a couple times, and I'm here, right? And if anyone wants to volunteer to do this part of our meetups, feel free to speak to Harry or myself afterwards, and we're happy to incorporate you guys into our work, right? Because this is all about us learning as a community, so, okay. Cool, so this was another thing that I've always wondered about. I've heard about lasso regression and ridge regression, and I've always been like super confused, like, what is the value add here? And I've always been like, okay, like how do I tell them apart? What do I do? And so I think that's a good question to kind of go over. All right, so let's start off with like ridge regression. Ward, you're gonna have to help me Google some stuff. So just make sure that I'm saying the truth because I left my notes. So, can anyone talk to me about ridge regression, what context they've heard it? Anyone want to kick it off for us?
It's regularization on top of linear regression.
Right, which type of regularization, L1 or L2?
L2, I think.
L2. So this is just a good, nice interview fact to throw in. This is an L2 regularization. It involves squaring the loss term, right? There we go. So you're squaring a lambda term.
Wait.
What?
Wait, the parameter is linear.
So
Not the loss itself, but that.
the additional parameter,
Yeah.
which would be lambda, which I
Okay.
wrote correctly. Full points on the board. All right, so I'm just going to leave this up here. So you generally have a lambda term that you'll add to your loss function. Can anyone read out the loss function equation? We all know what the loss function is on our impression, right? Mean square error, yes. Right. Why don't we just write it down one more time? Can someone just read it out? I just hate making myself look stupid. Harry, have you gone on yet?
Yeah.
Cool.
Well, isn't mean square error the sum of the square and the residuals?
Y actual minus Y predicted. Is it over n yet?
Yes.
There you go. So this is generally what we're trying to optimize when we're looking at a regression, right? We're trying to get this as small as possible. So you've got different techniques to get it as small as possible. There is a closed form solution for certain types of regressions, but some folks like to use gradient descent. That's become the big buzzword in the industry to try to improve our calculations, right? So like you take one step in one direction, you adjust your calculations, you keep going, right? And hopefully you get to a point where your mean square error, this is your MSE, pretty much, as you increase the number of steps, hopefully you find what is the global min in your sample space, right? So that's a pretty cool thing to just know, right? Maybe at some point we can go over optimization, maxing up the, like we can just go through
Maximum
various
likelihood.
maximum
estimation.
likelihood, various like of these, and we can just kind of discuss them at some point. Maybe we'll do that in another presentation. All right. So you've got your mean square error, and you've got a lambda term, right? And what's going to happen is lambda times beta, right? Right.
For
There's
ridge
a-
regression.
Yeah.
It's
Lambda
lambda times the sum of the weights
Sum
squared.
of the para-
So lambda is not squared.
Sum of the weights.
Some, let's say W is I squared.
I squared plus W2 squared, right?
Right.
And then it's the square is on the actual weights. It's not on the entirety of the weight, right? Yeah. Okay, good. So in this case, if I make lambda really big, right? What happens to my mean square error? It stops mattering, right? It doesn't really matter. So what's going to happen? I'm going to get a ton of bias in my linear regression, right? So it's going to get closer and closer to a flat line, right? Because I'm going to say, like, what's the best I can do? Probably a flat line, because I made this lambda, like, let's say 10,000, but my x values are like 1, 2, 3, right? All of a sudden it stops mattering, right? This entire mean square error is never going to get any smaller because my lambda is huge, right? So my parameters just don't matter. So that's one way to think about this. But generally, we keep the lambda at a very reasonable size, and we determine lambda by doing cross-validation, right? So we'll look across our various samples, break it up into 10 pieces, and then try to identify what lambda helps us fit the function the best, right? So then we take that lambda and then we run it across our entire data set, and we try to see, okay, what's the best mean square error we can get, given this lambda that we've already tested across our training data. Cool. So that's the approach for ridge regression. And then we also have lasso, right? So unlike ridge, you've got your mean square error, but this time, take lambda plus the absolute value of the weights, right? So this is just another form of optimization. And then there's another form of, and this is what we call L1 regularization. I think these are just given just for simplicity. People like to be like, oh, it's L1, oh, it's L2. It doesn't really matter that you know this, but it's just a nice thing to say if someone asks you. I would just always remember this is L1, because this one kind of looks like an absolute sign. So you can just say, kind of, maybe, it might be.
It's the absolute value.
Absolute value.
Oh, it's the absolute value each. Thank you guys. Right, because it was a square of that absolute
It's like
value.
first order L1, second order L2, so like square of L2. So power, first power L1, second power L2. You can think of like L6.
Yeah, that's a good way to think about it, right? And remember, half the battle is just remembering this stuff when you're in an interview and you're like, what does it all mean, right? Okay. So this is pretty interesting. This is really useful when you've got continuous variables, but what do you do when you have discrete variables? Now that becomes kind of an interesting challenge to think about. Let's say you have a case where you have an experimental mouse weight, and you have something like diet, and you have normal, and you have like heavy fat. Right? So now, this, so it's a little, right? You got something like this, right? So how would you regularize in this case, right? Is there a need for regularization in this case? When you just have two means and you're looking at two variables, two discrete variables. What makes sense?
0, 1. Having like number of extra variables, one for each. Something like this.
Right, if I was just making this equation, I would write like y equals like beta naught plus like beta 1 x, right? You'd only have one term in there because of the dummy variable rule, right? Because you don't want any of your coefficients or any of your terms to be a linear combination of any of your variables, right? So you gotta be careful about that sort of thing. So then you can stick something in here. We'll call this, let's say, diet difference. So if my x is, let's say, did I have a high fat, right? Then I would say like this x would get replaced by a term that's like diet difference. So if x equals 0, then I had a normal diet, right? And I'd just be calculating the mean. Or if x equals 1, then I have this other mean, right? So in this case as well, you can run a regularization. You throw an L on the term, and you see like, okay, can I optimize even this case? Does it make sense if I look at a cross-validation strategy? And you can actually apply the same terms here. Now it's more relevant when you have multiple terms, when you start mixing the terms, right? So let's say you have like birth weight as your other variable. So now you've got two sets of data, right? You guys are just gonna have to work with this, right? Assume these are x's and these are dots, right? So let's say x is for like normal, and the dot is for heavy. And let's say these are like, this chart is of like birth weight. Now I'm trying to compress something that would ostensibly be on 3 axes into 2 axes, so do excuse the illusion. So what am I trying to do in this case? I'm trying to predict lines that will make sense. Of course, when you're doing a linear regression, I'm trying to predict one line, but I have compressed an axis, and I'm trying to just show like visually like what it would look like, right? So what do I have going on? Let's just summarize this. I'm looking at the birth weight. I'm trying to determine the size of this mouse on this diet, right? Birth weight is continuous. Size is where I started it, and then I've got 2 different sets of diets that I've applied. So I've shown the X variable as my normal diet and .heavy as the heavy. Make sense? So this is a case where you would have an equation where it would be like y equals beta naught plus b1 times diet difference plus b2, right, times birth weight. Right. So this is a case where you want to make sure, where you might want to apply regularization and figure out like, okay, what's the optimal values that I can get for this regression that don't overfit the data, right? So just to round out the conversation, just to make sure that I'm coming back to fundamentals, we've all heard the terms bias and variance, yes? Can anyone define bias for me? Jacob? Not yet.
What was the question?
Huh?
What was the question?
What is bias and what is variance?
Variance could be how far away you are from your target.
True, but I'm trying to look. Okay. Assume I have these 2 plots, right? Which one of these plots shows higher variance and which one shows higher bias? And let's use the diagrams to kind of figure out what the meaning is. Because I always need like an intuitive photo to kind of do this. So like, what do you think this one is? Higher bias or higher variance? Variance, right? That's pretty obvious, right? This thing is moving all over, so therefore there's a lot of variance on it, right? This one's going to be biased because I always think of bias like I just don't care and I'm going to just do what I do, right? So that's bias, right? Because this one is kind of not becoming, it's not adjusting to the data as well. And so I kind of think of bias as this idea of you already have like a preconceived notion, and so the data doesn't actually affect what you think, right? So when you have a high bias case, it might fit the test data better because this variance might be too much in your training data. So when you try to apply it to your test data might be like, but dude, we're down here, right? Because in reality, your test data can be completely different than your training data. When I was a machine learning engineer in a startup a while ago, like we thought we understood what our customer knew, what our customer wanted, but we actually had no idea. Like the responses we got on our customer support system completely different than what we actually ended up seeing. So you have to think like, okay, in that case, would I want a high bias model or a high variance model? 2 is variance. Stop messing with me. I was like, did I miss something? Right. So again, what does this come back to? So if someone said like, why would you want to regularize in the first place? You say, well, I want to make sure that I'm fitting the best model to my data, and that by adding a term that forces it to have less variance to my trained data, I hope I can fit my test data better, right? And the best part is you can do your model with regularization, you can do your model without regularization, you can pick one, and you don't have to tell anybody about the other model. Just throw that one out. Problem solved. Was this helpful? So continuing on, what are some other questions that we could discuss for next time? Like, is this a good level of discussion? Do we want to go into a different area? Are there any questions that you guys have you want to explore in our next meetup?
How about optimal pandas practice?
Optimal panda practice, that's a great one. Like, I didn't understand pandas indexing for the longest time, and I wasted so much time because I just always ignored it, and I made it like 1 through 10, and I was like, whatever, right? Or like working with group buys and doing some really interesting things with them. that's always a good thing to do. It just makes you feel smarter, move faster, get into stuff. Anything else?
Elastic net. Elastic net.
Elastic Net, like the Amazon, so wait, what's that?
No, that's it. Kind of both one and L2 together.
Oh, do you mean like that, yeah,
Yeah.
another form of program, yeah. So, yeah, we can go, yeah, that's elastic, what's it called again, elastic
It's
net?
elastic net. I think it's like some combination.
Right, it's just a combination where you do like your L1 plus your L2, and you just have ready to go, right? So you just do your, and basically, it's supposed to provide, it's just like another thing you can try out. Again, the best part about data science is no one really knows what's going to work on your data. So I try out every single model, and then I just pick out the best one, and I look like a superhero, and I don't try to make up stuff as to why it worked. Because sometimes you get lucky. What? Douglas.
Douglas is up.
All right. Douglas, you're up.
Does the microphone work?
Hello? So I feel like we get a very different crowd every time, every meetup. So I was wondering, like, what are you guys' experience with machine learning and like things like NLP? Experience with machine learning, just in general. About a third, a half. What about experience with natural language processing? So here people. And what about deep learning, neural networks? That's what it counts. So I tried to keep it pretty high level since this competition was already over. But feel free to ask questions if something, like I'm assuming basic experience with NLP and machine learning. So if there's any parts that are unclear, feel free to ask. All right, so let me introduce myself. My name is Douglas, and I'll be chatting with you today about the Quroa Kaggle competition. Since this competition is over, I'll try to not overfit to this competition and just give you things I learned that might be useful for future Kaggle competitions or data science projects. But this wasn't a very active competition, so feel free to check out the grid kernels and discussions that are on the website. So for those of you that are unfamiliar with Quora, there's a platform where you can ask a question and people answer. One interesting thing from their about page, Quora helps you understand why the world works the way it does and why people behave the way they do. So one interesting thing is that Quora is okay with controversial questions to get different viewpoints, but they don't want loaded questions that are really just a statement and not a question. So a quick outline of my process. First thing is to do some data exploration to see what's in your data. And since this is text data, we're going to do some natural language processing. And finally, I'm going to build and tune a neural network because it's shown to be pretty effective in dealing with text sequences. So, and first step to any problem is just to get to know your data. So the data set only has 3 columns: the question ID, the question text, and the target label. With classification problems, you want to see what your class distribution looks like. And here we notice that there are very imbalanced classes. Only 6% of the questions are labeled as insincere. This explains why the competition's evaluation metric is F1 and not simple accuracy, because it's going to be very misleading if you just use simple accuracy. We also notice that it's a fairly large labeled text data set with 1.3 million questions. So that's pretty impressive for text labels, since it takes a lot of work to label these subjective kind of text data. Also, because of the class imbalance, you want to start thinking about techniques like adding class weights to adjust your loss function, and also oversampling. What I ended up doing was doing a threshold search for the best threshold to round off the predicted probabilities from the sigma activation of my model. So it's always important to look at the individual questions that you're working with. So here are some examples of insincere questions. In a situation like question 1, where a bad word kind of makes the question insincere, a bag of words model may be used, can probably classify this correctly. With examples 2 and 3, it's kind of more of the grammar and kind of statement making that makes this insincere. And so bag of words might not be enough to capture the information in the sequence of words. Yeah.
Sorry, I don't mean to like crash your meeting, but is it okay to ask a question?
Sure.
So I'd worked on some of this a long time ago, so I'm very curious, like, did you only use the questions themselves, or did you also look at the person asking them and their history of insincerity, so to speak?
Sure.
There's no way to
In Quora?
yeah, for the data set.
Oh, this was from a data set. Sorry. I thought you were taking it from an API. Okay, no worries.
Yeah, for this data set, they kept it very simple. It was just an ID. And
They didn't even give, did they tell you what questions came from the same person? You didn't
No,
have-
not.
Oh, I see. Okay. Okay, cool. Thanks.
So there's, you could definitely do some text feature engineering, which we'll talk about. But to continue, there's another branch in the problem if you look at question example 4 there. So you might think this is insincere, but it turns out the label is actually sincere. And so it turns out that the target labels are not totally reliable. And the competition mentioned this too, that the ground truth is not always the ground truth. So with those things in mind, let's move on and we'll process the data. Again, since our only feature is a string of text, we need to do some natural language processing to get it ready for the modeling. In this case, I did minimal pre-processing. In other cases, you may want to do a lot more pre-processing, and some Kaggles actually did that. They made long lists of misspelled words, fixed the punctuation, things like that. For me, I wanted to preserve some of those misspellings and weird punctuation because they can signal low effort, and they may be an indicator for insincere questions. So all I did was actually just normalize the Unicode to get rid of some weird characters. And then I used Spacey to tokenize the questions. So tokenizing is splitting up the list, the string into individual words so you can work with that. And I use Spacey because it has special cases that built in for like contractions, unlike their basic scikit-learn and keras tokenizers. I did use the bare bones version of Spacey because of time constraints in the kernel. So I didn't use any of the fancy parsing features for like noun, pronouns, things like that. So you'll be fine using any of the NLP-focused tokenizers like NLTK, text block, things like that. But I did still use the keras tokenizer because I wanted to build a word index and encode the sequences for feeding into the model. And it turns out that the keras tokenizer can accept a list of already tokenized words and just turn them into integers for you. So that's pretty nice. So I was trying to reuse code that someone already wrote. And so going to the text features, before I encoded the sequences, I generated the text features. Although neural networks do a lot of feature engineering for you, it's always useful to give the network a higher level signal that you know you want. Some of the interesting ones are metadata, like how many tokens there are in the question, and also the percent of the tokens that were in all caps. As you may imagine, yelling, this emphasis on, that may have some signal for this insincere classification problem. There were some people who did a lot more feature engineering with the text, but they mentioned that only basic features had much signal for them, and I didn't have much time to try all their permutations, so I left it at only a few. But the features that I did use gave a solid 0.005 boost in the score, so they are useful features. Now, what are embeddings? Embeddings are vector representations of a word in a lower dimensional space that exhibit latent semantic properties. So there's a famous example of king plus female equals queen, that kind of semantic property. And often you want to learn an embedding space specific to your task because you want the stop words and things like that to be representative of your corpus. But in this case, I felt there wasn't enough context in the short questions for that to generalize well. And when I tried to use the corpus-specific embedding, it quickly overfit to their training data. So that's why the competition made 4 pre-trained verb embeddings available for us. First is their famous skipgram model, Word2Vec, which kind of put verb vectors on the map. But that suffered from poor token coverage in this problem, so I didn't use it. And then there's FastText. I was really excited about this model from Facebook because it featured subword information to generate vectors for other vocabulary words. Unfortunately, the competition only gave us the plain vectors and not the binary model with their subword information. So this didn't turn out to be as strong, as helpful as I would like. And there's paragram. From what I understood, the paragram vectors came from fine-tuning Word2Vec vectors using a paraphrase database that was filled with pairs of similar phrases. I thought it performed fairly well, but one thing to note when you're using it is that it takes all lowercase tokens, so you need to pre-process the text more. And last but not least, there's GLOVE, coming out of Stanford, which stands for Global Vectors. It has 2.2 million tokens, and I found that it had the best coverage and the best empirical performance in the classification. So that's the model I went with. But people also tried ensembling by concatenating the weights from different embeddings. So 2 300-dimension embeddings might be concatenated into one 600-dimension embedding. And other people try to average the weights. One thing to note is that the state of the art of embeddings have now evolved to contextual models. So you could tell between one word that was being used as a noun versus a verb. So there's like Elmo and even Bert, which is trained on bidirectional. So these are not available for the competition, but it'll be useful to learn these for your own NLP test.
I have a question.
Yeah.
What do you mean it wasn't available for the
So-
competition?
So the competition didn't allow outside data except for the 4 embeddings.
Oh,
Yeah. It was also a kernel-only competition, so you don't have as much time to run all those models. Like with the fancier parsing, it takes a lot longer to parse compared to just looking up fixed embeddings. So that's what I'm talking about in this slide, is how do you actually use the pre-trained embeddings that you were able to load in. So one way to do it is to randomly generate an array that is normally distributed around the mean of the pre-trained vectors. And then you replace the random vector with their pre-trained vector if your token is in their matrix of their pre-trained embeddings. So you get something that looks like that. And finally, you can pass this matrix as a weight to the Keras embedding layer. Something important to note is that our vocabulary tokens will keep the randomly generated vectors like this, like the parsing gray. So the random seed can have a significant role in your embeddings. And now onto the neural network. So I won't go over my exact architecture because that's a hyperparameter in itself, but I'll mention a few considerations. First up is the Keras versus PyTorch debate. So people in this conversation were saying really good things about PyTorch, and a lot of people switched over. Personally, I stuck with Keras because I'm more familiar with it from past projects and also reading Cholet's book. But one big reason why people switched was that Keras GPU layers were not deterministic, so it was leading to unstable results, whereas PyTorch was more stable. And for this competition, the CPU RNN layers were just way too slow to run for this competition. Next, RNNs are traditionally unidirectional and they're forward-facing, but text sequences really benefit from a bidirectional layer where the network can access context in both directions. And finally, there are two major forms of recurrent network units. There's GRU and LSTM. From what I saw, they perform basically the same, but I did read that GRUs are slightly more efficient computationally, while LSTMs might be perform better for longer sequences. And another thing I spent a lot of time on was optimizing the learning rate. So apparently this is one of the more important hyperparameters that you could tune for your neural network. And a new technique I learned was cyclic learning rate. So the idea is that you cycle through a range of learning rates and you alternate between increasing and decreasing. And this, going back to Andy's discussion about doing a gradient descent, this helps you break through local minimum and also get to saddle points in the gradient. And you do get some temporary increase in loss, but the goal is that you ultimately get to a lower minimum. While the idea was very cool, I found the simpler reduced learning rate on plateau callback to be more effective for me in this composition. The idea is that once you think you've gotten to the general vicinity of the minimum, then you start taking smaller steps. And rather than continue to bounce back and forth like on that graph below. Yes.
How is this? This is the first time I've heard of cyclic LR. How is that compared to simulated annealing? Do you know about that?
How does that work?
Simulated annealing?
Yeah.
Like, is it the same?
I'm not totally sure.
Okay. It sounds similar.
Anyone else know about annealing?
What's your question?
Simulated annealing, and how is that similar or different from the cyclic LR approach to bounce out of local or maximum or local minimums?
So it's been a long time since I've done that. Simulated, did that use like hill climbing techniques?
It's
With
more
that? So here it sounded like it was just moving between the maximum and minimum, but there was no randomness, right?
Yeah, that's a probability. If you increase like energy, you have probability going there versus just going down.
Yeah. Well, and here you cycle between high learning rates and low learning rates.
Right, but here you hope that high learning rate will kick you out of like a situation where you may stuck just by being like, larger steps.
Okay.
Over there it's more like you're always going down, but some probability can go up. That's my understanding. I don't know if that's it's more like the Quora stuff.
It looks like simulated annealing is just like kind of sampling from all over the place. Whereas with this like cyclical learning rate, you're going through like, you're training your network in the same way you normally would, but you're just updating your weights with a modulating magnitude. That seems to be what it is.
Yes, over there it's like random steps, and you see if it go down or up, right? Well, here it's like bigger steps towards minimum, but then it kind of move you through start position. But, okay.
I'm not sure.
Yeah, like for the reduce LR thing, as you take smaller steps, it'll be harder to let you do, you'll move slower basically. And the cyclic, taking bigger steps occasionally might get you out of a minimum or just move things faster. Okay. So another thing that I learned from this competition was something called a capsule network. Apparently it worked really well in the toxic comments competition from a while back. And it's similarly promising, I didn't quite understand fully to use it in my model. But the idea is that you replace a more primitive pooling layer that you use to with something called a capsule network, and which would couple lower and higher level features. So if the lower features agree with the higher level feature agrees with the lower level features, then the signal gets amplified for a positive feedback loop. I have links in the resources if you want to read more, and I'm still trying to understand it fully myself. But the idea is that you get some collaboration between different layers. And after all that work, let's look at some results. Of course, this is all an iterative process, so I've been looking at the model performances to make adjustments in adding features and changing network architecture. There was one team that did an impressive job in their public leaderboard. They got 0.878 F1, whereas the rest of the competition, they topped out at about 0.71. So very interested to see how they did that and how they will do in the private leaderboard, which will be coming out in about 2 weeks. From the discussions in the competition, other people said that their CV scores, the average CV scores were about 0.7. Of course, I was still very far from those top performers, so there's still much to learn. Now, F1 is great and a very helpful metric to see how well your model performs, but it is still just a number, and the real value is whether your model can detect insincere questions. So we'll take a look at our example questions again. So with question 1, it was classified correctly, as you may expect. Question 2 was also correct, but you can see that from the probability that it wasn't as sure anymore. And this is where the threshold search came in handy, in that by lowering the threshold, you can actually still pick up the signal and classify it correctly, even though it wasn't as sure as like the first case. And then in question 3, they actually got it wrong. But you can still see that it's picking up that it's kind of borderline. Their average best threshold was about 0.33, something like that. And finally, it was very confident that number 4 was insincere, like we might expect to, but it was scored wrong because the target label was sincere. So some other more general Kaggle takeaways. Kaggle now has free GPUs, so it's very useful if you just want to play around with GPU kernel with public data. I did notice that sometimes it's not on even when it says it's on. So I would do a quick check before you commit your model, so you don't waste any time, and you just reload if you don't get a GPU. And also, Kaggle has limited resources, so GPU kernels are restricted to 2 hours and CPU at 6 hours. And there's also some memory limitations. But it's kind of nice because in the real world, you're not going to have unlimited resources, so it's kind of nice to have those constraints. And I think we might want to get used to it because Kaggle is seems like they're hosting more kernel-only competitions nowadays, so you might have to work within these limits often. And then you want to write robust code, because you don't know what can happen in the unseen data for your final private leaderboard set. And so you want to fill NAs and just do error catching in general. So minimize your hard-coded variables, things like that. And finally, the dangers of overfitting. So you don't want to overfit to your test set, even though it's very tempting to get your public leaderboard as high as possible. So you want to get some good cross-validation schemes set up for your training. And that's it. Thanks for listening. I hope you all got something out of the talk. Again, my name is Douglas. I am looking for data science opportunities, so feel free to reach out. It's my LinkedIn and email. And my domain knowledge is actually from animal production, but I do learn fast and yeah, eager to find value out of data. Cool. Thanks for listening.